another inspection. It's already for Monday.
Yeah.
So what is preventing you from finishing it?
Well, we're working on it, but
The weekend is a long time to work on a project. So how is the homework coming up? Is there the homework?
well, the thing is, like, yeah, you're getting stuck on some parts, and it takes a lot of time. You go from office hours and stuff, and
Okay.
you know.
Okay. Well, work on it hard and then ping me on Sunday to see where you're at. So at some point it's a time management issue, okay? Because computational projects or any projects, they take a long time to complete. So it is at some point your decision that in the competing environment of last homework in any course you take is going to have a last homework that is due next week, right? Including this one. So there's other studying going on. And yes, it bothers you that it's not working in a certain way. But at some point, it is also simply okay to decide, okay, this is going in the way it is. Okay? So work on it hard enough and make a plan. Budget your time. If you were preparing for next month or for a semester or whatever, you have a budget. You know how much you're spending on housing. You know how much you're spending on food, or at least how much you have for food. You have how much you're spending on clothing and all other things in life and going up. So with all of that budget, and I hope you have a budget to plan for these things, right? So when somebody asks you, can you go, do you want to go out for a party or movies? A, that has a money attached to it and it has time attached to it. Do you have the time for it, or is it your priority right now? And in the next week, probably not. Okay? Like 2 weeks maybe? And so how is your time best spent and how is your money best spent? So same thing goes here. And it's not the end of the world to submit a project that is like 90% there, but like that last thing you just can't get to work. But then you step back and oh, this is 90 points is a good score, right? So I'll let you budget yourself over the weekend a little, but also look at your weekend and say, these are the 3 competing things I need to do this weekend. I need to sleep too, I need to eat and relax a little bit. How much time is allocated to each? Okay? And then spend that time, and at the end of that time, simply evaluate, do I want to keep going with this project? Okay. Or do I want to stop and turn it in for partial credit of some sort? And again, it's not the end of the world. Okay? So do your best, and then if you still need an extension, I'll allow you an extension. I actually typically don't mind. But is it your best interest to actually keep working on it? If you're really so involved in it, emotionally, that you really want to get it done, then probably yes, because you're not going to be able to sleep otherwise. But, right? But then that's your decision to make. Okay? So budget your time over the weekend, then spend that much time that you have on this versus something else. And then after that, if you need an extension, I'll probably say yes. I can tell you right now, I'm soft that way. Okay? But it ultimately doesn't bite me as much as it does. Okay? Because again, it's the last week of the semester, so there's all other competing things that you need to spend time on. And you need to start thinking about preparing for exams as well. Okay? Okay. So now that we got that out of the way, that you know that I'm soft, deadlines are good in certain sense because they kind of get something done and move it out of the way, okay? So that's what deadlines are good for, because you do need to move on. All right, so just a quick wrap up on curve fitting. You will have what I hope is going to be a really exciting homework because it's actually going to use field data. Somebody had fun and called a field Longhorn Field in Louisiana. Field Corp did that. Like Texans are working on this field. So there's data from curve fitting to fit, the major part will be fitting permeability and porosity data. I mentioned already that permeability is a function of porosity, but not just of porosity. So that gives us this data scatter, so we cannot exactly predict it based on porosity. Typically, we need also grain size at the very least, but grain size is not something easily measured always, and it's not something that has a single number as a measure, it has a distribution. And then it's a very good question, how do you incorporate that distribution into your model? So that will give you a data scatter, and that's where actually curve fitting or striking a trend through the data, maybe curved trend, maybe straight line, actually helps out. So you will be given a model in there. The last question is called Femur Coates model. It's one of the more used models in formation evaluation to actually predict permeability. For permeability, we don't have a bell log that is easy to do. You can measure permeability. There's literally a little device that goes and kind of attaches itself to the open case hole, and it tries to inject fluids and see how fast it goes, right? But you need to kind of stop the operations, and it's time consuming, and it cannot be done continuously. Okay, you do that at a number of locations, but you don't have a continuous permeability log. Okay? So nowadays there are some digital methods that are coming along for that, but it's in the works. So predicting permeability is the most important thing we need to do. How fast does it flow out? That's the porosity and saturation tell us how much is down there, and permeability tells us how fast can we get it out. And that's basically what this business depends on. So in that sense, predicting permeability is one of the more important things to do, and you will get an exercise. So the model is given. That model has some parameters, I believe 3, and then you're supposed to basically figure out how to use everything that you know to find those 3 parameters. So just as a quick recap of curve fitting, so key thing that we need to know is we need to know what the model is. So in this case, I'm attempting to strike a line. That's the simplest model there is. It's called linear regression. And that model has 2 simple parameters. We call them A0 and A1. I could have called them anything else. And the way we go about any of these is essentially, okay, this is my model. So there is an error between the actual data point, like for instance here, and whatever model would give me for that particular point x, right? So there is a difference between the two. I square that difference, sum them all up over all of the data that I have, and then I attempt to minimize. This square business helps me out because it's essentially a parabolic relationship, and I can find a minimum for a parabolic relationship, so that basically gives it a unique minimum. And then based on that minimum, I find what my model is. Now minimum, just like in finding a minimum of f of x, you will look at f prime of x is equal to 0. In this case, you have a function of however many parameters you're looking for. So if it's 2, you're going to take 2 partial derivatives and set them to 0 and find the parameters that make that happen. So let's actually now, so that was the linear regression where I had, just a simple relationship y versus x. Just to get an idea of how it happens, what happens when you have, we did a polynomial. So let's say that we have multiple linear regressions. So I said that permeability is not just a function of porosity, even though you will be busy figuring that out in your homework, but it's the, for instance, function of grain size too. So technically my permeability could be y, and my porosity could be x1, and my grain size could be x2. Okay? And then I'm looking, the simplest relationship I can always look for is linear. Okay? That's the simplest thing we know how to model. In any kind of scientific / engineering endeavor, you go for simple first. That's an easy picking. If that doesn't work, then you move on. So do the easiest first. And in the easiest case, I'm just striking it. So linear in this three-dimensional world means a plane. Okay? So basically this y is some number a0 plus some other number a1 times this first unknown, and plus a2 times x2. Okay? So that's the linear relationship, and that's the definition of a plane, just slightly rearranged from whatever you did in your, was it calculus class? One of those math for 20-somethings, okay? So they do come in useful. Okay? So now that is my model, and that model has how many parameters? 3. I have A0, A1, A2. Again, how I call them, it's up to me. Here we're just kind of numbering them with A's. All right, so that is my model. So my error is this measurement yi. So I have x1i, x2i, and yi. I have triplets of points of data. And technically, I could keep going. I could have 7-tuplet, which is not, we're not going to call it 7-tuplet. What's a 7-tuplet called? Septa something. You go to so quintuplets is 5. What is septuplets? Septuplet. All right. Some sort of Latin version of 7. Okay. So you could choose 7 of them if you had that much data, but that would also mean 7 parameters. And you would take partial derivative with respect to that parameter. All of those. So if it's 7 of them, you would get 7 equations. So in this case, the procedure is always the same, really, and it's just working out the math. So if I took the partial derivative of this SR with respect to first parameter, A0, that's going to give me the first equation. Then partial derivative of SR with respect to A1 equals to 0 is my second equation. And then partial derivative of this SR with respect to A2 is my third equation. And the only hairy part is that I have these sums that I have to drag along. But they're sums of the stuff I know. I know yi, I know what x1i, and I might have 3,000 of them, but I know them. Okay? So they're not variables, they're known entities. So when I take derivative, they're kind of simple constants, right? They're not bothering me. So when you work that math out, so these partial derivatives, you're going to get something like this, okay? So I have square, I take the derivative, there's a 2 in there, there's a minus 1 in case of A0, right? It's minus x1i in case of A1 that shows up, and minus x2i that shows up in case of A2. And then I'm going to clean that up a little. I get 3 equations for my unknowns A0, A1, A2. And this being linear regression, it's just with multiple variables. It's again a set of linear equations. We will not get away from linear equations or systems of linear equations here. So essentially, I set these up. If I have the data, I can easily compute these sums. Okay? And then this is a 3x3 matrix of numbers. Those sums are still just sums of numbers I know. Okay? And on the right-hand side, I have sums of numbers I know and I can compute. Okay? And then I find, with my favorite linear system solver, if I can find the one I programmed, I use that. If not, I use linal, np.linal.solve, and I solve this for A0, A1, A2, and then I have a model. Okay? So these things are actually, when you go to Excel, they're actually available. You can highlight the columns you want, and you can click on the type of the relationship you want, and you will get these models and how they're quickly. But part of this course is knowing the mechanics of how you do that. If Excel, most likely, does not have Femur codes model in there that is relevant in information evaluation. So you need to know the mechanics of how you basically get there in order to fit it, okay? And that's going to be exercise of your homework. So again, no matter what, you need to know the model first, then you go through the procedure. If it's linear like this, it's easy. If it's nonlinear, so if it's any kind of power relationship to the data, okay, we essentially take the log of both sides of the relationship and figure out whether I can transform my variables to get linear relationships of these transformed variables, and I can still use the same code, okay? And that's basically what you need to know. So again, any kind of power law relationship, take a log, see what happens, okay? So that's essentially wrapping up our linear regression or fitting of the data. And we're gonna move on to our final topic, which is differential equations. Maybe next to final, I will probably have some time to go over numerical integration as well. Open. Okay. I know for a fact that differential equations is your favorite course so far. Isn't that true? Isn't it? Well, good news is that I'm going to give you a way out of that course. So what you learned in that course is not relevant here other than that you know that there are certain classes of equations that allow you to find out an analytical solutions. They're definitely important, but there's an entire rest, which is basically 5% of the cases you can find an analytical solution. In 95% of the cases, especially in petroleum engineering, you cannot. Okay? So this is the importance of numerical methods. So knowing those equations in analytical solutions is still very important to verify my numerical methods. But after that, after I use analytical solutions to verify them, I kind of let my numerical methods loose and let them solve the problem that I cannot get analytical solution for. Okay? So that's basically the procedure. Okay? We devise numerical methods. You can analyze them and figure out how accurate they are. We are typically avoiding that in this introductory course, but there's like an entire line of inquiry that tries to figure out how good these methods are and tries to measure their accuracy. But we're basically just figuring out, well, what is the basic procedure to actually solve cases where I cannot find analytical solution. So let's get going. Here's an example. Let's say that I have a tank of water, and the tank has a little spigot at the bottom, and the size of that hole, as well as the height of this water, the height gives me the pressure that I have in the tap, and as my height is changing, so is the pressure. So I have this dynamically evolving situation, right? So basically how much discharge I'm going to have kind of depends on the height. So if I'm trying to look for one or the other, I have a problem because it's not a simple relationship. So basically, how do we go about? I have some influx, and also there's also influx. Now this is something that I know, so I'm just throwing the water in. And let's say that I have a function in time. These are some parameters, K1, K2, and C that I do know. Okay? And there's some periodicity to it. Stuff is coming inside. So this is how my influx is changing in time. Great. Now the rate of flow depends on height, and somebody who took transport phenomena already has given me this equation. This is how it depends on the height. So there is a square root of h dependence on how much is stuff going out. Again, I have this A pipe, this actually a hole should be. So this I know, this is density of water. 2 is 2, G is gravity, 9.81, and height is something that is constantly changing, so it's one of the things that I don't know in this business. Now, how I'm going to solve this problem to get the height, or to get the equation in height? What has to be true for a steady state problem here? When I'm engineering things, what am I aiming for? Equilibrium means what comes in. Okay, that's your, if you learn anything in this department, good engineering requires that what comes in has to come out. Huh? Or if I'm actually looking at the change and monitoring that change, okay, then basically my change in mass, so that I don't have overflow or like things like those. So if I want to just look at that, that's basically what's coming in minus what's coming out. And in good engineering, that should be 0. That gives me a steady state. Or at least this change in mass should not overflow that tank over there. So I might need to engineer the size of this entry here accordingly. Or a size of the outlet. Great. Okay, so basically, the mass of stuff in the tank is actually related to this height as well. Okay? So mass is rho times volume, right? And volume is area of this tank on the bottom times height, correct? This is a cylinder. So basically, this is the change in mass when I replace mass with rho times volume, area times h. Yes? So this is essentially my equation for height, transient equation. If I want to look for steady state solution, I will zero this out. And then this becomes a root finding problem. But if I'm not looking for steady state problem, okay, then I'm looking at the transient behavior. So early time versus late time. As an engineer, even if I'm aiming for steady state, I can't get it immediately. Things don't just instantly happen. We don't have a wand that says, poof, you now be h is equal to 3 meters, right? That's not how it works. You gotta get there. Right? And this get there part is called transient time, and it's basically governed by this equation. So if I might be looking for early transient time behavior or for late behavior, which is my desired steady state. So in that case, I gotta solve an ODE for this transient behavior. However, this is not an ODE that you can easily solve using your knowledge from differential equation. Even if you got an A, you might have some issues. Okay? So because there is time here, cosine of time, some constant times time, and there is h. So this here is a function of both time and h. Yes? And I'm looking for h. So my change in h depends both of the time that has passed, and h is a function of time too. So this is something that makes this relationship really clear. So great, we're going to learn numerical methods for this. What I also need in any kind of solving of these problems is what's missing for this to be a fully defined problem. How do I solve something at 0? What I need to have maybe h at 0, right? So I need to have some sort of initial and boundary conditions involved to actually solve. In this case, initial conditions. So what am I starting from at time is equal to 0? Time is a relative thing when I'm going to start at 0, right? So I can, it's up to me. So I start at some point when I start the clock. I call that time is equal to 0. Okay? And at that time, I started with certain height, or maybe with 0. I don't know. Maybe there was nothing in that tank before, but that depends on my case. So given some initial condition, we can go and solve this. Okay? Great. So quick, then this is basically, I have just defined an initial value problem. So I start from certain value, and then I march forward in time, and I'm looking for the solution in time. boundary value problem was that rod that we had, okay? I had my boundary set to certain temperature. It was the case of a temperature. And there was that heated rod, and I was keeping ends at different temperature, and I was wondering, given that it wasn't insulated, how is it going to change in time, because ambient air temperature was much less than what I had, okay? So that is a boundary value problem. Either way, I have an equation that I'm solving, and I have either initial value or a boundary value that I'm looking for. So there was no time in the boundary value problem that we were solving. Great. So there's just a matter of definitions. This is a review. So if you have a first order equation, what that refers to is how many derivatives you're taking. So if you're taking only first order derivative, dy versus dx is some function of, in this case, this is now a function of x. So then you have some function of x and y here. That is a first order equation. Second order equation has a second order derivative. Okay? So order refers to the order of derivatives you have in the problem. Now, we are not going to go into partial differential equations, but that's basically when I have multiple parameters I depend on, and I can take derivatives with respect to all of them. Okay? This is just to give you a taste how we solve these problems. So the problem that we're going to be concerned with here is initial value problem. So I'm going to switch from those time and age, because that was a specific situation, to something more generic. So I'm going to look for a function y of x, and derivative of y, or change of y with respect to x, is equal to some function of both that x and the function y, which is also y of x. So here, what I really have is f of x and y of x. So this is my generic problem that I'm solving. And again, we're going to walk through different type of methods that are solving this problem. And you will get an assignment for a specific case, please solve this, right? But the methods should be generic, and there should be essentially a formula that you kind of apply, and the process that you apply to solve all of them. So we also have to have some starting point value. So we're going to typically have y of x is equal to x0 is equal to y0. That's my initial value that I'm starting from. So after that, we're going to iterate. Okay? So we're going to start from that initial point, and we're going to sort of discretize the space x, and at next point we're going to try to find the value based on the previous one that we had. And we're going to attempt to use this differential equation to tell us how to approximate. It's not going to be exact, it's going to be approximated solution. So simplest solution ever, always of them all, is to take that next value, yi plus 1, okay, as my previous value that I just had, and then some slope phi times spacing h in between. So h is now spacing between my x values. Okay? So here's how it looks like. Basically, I start from some previous value I had. I always kind of label those xi, and next one is xi plus 1. So this is my spacing h between x values. This is this function that I don't know, but I'm trying to find out. Okay? And I right now start like I have either a value here or an approximation for it, and that's what I'm starting with. So this is xi, yi. Okay? And then my next point is this old value yi plus slope times this distance here h. Okay? That's the simplest kind of approximation. And it's an approximation, it's not exact. So this is my actual value. And this is my approximation. And I'm going to try to close that gap, but that's what numerical methods do. They look for approximation. Okay? Great. So what is the simplest thing that I can do to actually find what this slope should be? Should I take this slope, that slope? How do I find slope? Well, the simplest thing I can do is literally take a slope of this function here at that point. What I'm doing is I'm saying I'm approximating this complex function with its linear version. Okay? A tangent to it is a linearized function, just a linear approximation. Okay? And do I know the slope? Does anything in my differential equation give me that slope? What is the slope of function y by definition?
Rise over 1.
dy dx. dy dx. So the simplest approximation for the slope is actually given by this differential equation. It's this. This I have. This thing. Okay? It could be something like this. Okay? That's what I'm solving. So that's the simplest thing I could do. It's crude because I'm just approximating, however complex this function is, I'm just approximating it with a line. Okay? But as I said, the simplest thing we always have is linear approximation. And the first person that figured this out always gets the most credit because those are the simplest methods. So maybe they're called Darcy's law. In this case, it's Euler, okay, that did this, Leonhard Euler. And they said, okay, great, this slope is actually dy dx at the point that I'm at. So evaluated at xi, yi. Okay? So at this point, based on the equation, I know what the slope should be. So then I take that slope for a ride to a new predicted value at my next xi plus 1. And of course, the closest I get between my point xi and my next point xi plus 1, the less error I'm making. So I shouldn't take this leap too far, right? Because my function has a chance to change. So this is my formula for my next value. Yi plus 1 is yi plus f of xi yi, which is the slope phi times the step size h. So this h is simply difference between this xi plus 1, my next point where I'm trying to look for a value, and xi. Yes?
It seems a lot like Newton-Raphson.
Hmm?
It seems a lot like Newton-Raphson.
Yes.
Taking the slope and then
The
evaluating.
difference in Newton-Raphson is I'm looking for that one point where the function is 0. So I'm kind of stepping towards it. Here, I'm not looking for xi plus 1. Those are given, and I'm looking for the value of the function y at those points. So I'm missing the entire function. So yes, it looks very similar, and guess what? This is actually a chopped down version of Taylor series, which is what Newton-Raphson is as well. So all we know is always just Taylor series. Remember, the most important thing you need to take from your calculus is Taylor series. Okay? In one dimensions or multiple dimensions, either way. So this is really what's this doing. This is xi plus 1 minus xi, this h. And this is your dy dx. So this is first two terms of Taylor series. And the second order and all those are chopped off, right? So you just chop it down. So it's a very simple idea. You're just exploring Taylor series for that function. Except that like your objective is different. In root finding, you're finding a 0 or a function and you're trying to step towards it. Here you're just trying to find function values at equally spaced terms. So in that sense, we're not going to look at error between these 2 points because this is an estimate at a different spatial point. Okay? So yi is an estimate of function y at xi. yi plus 1 is an estimate of function y at xi plus 1. So error between them doesn't make sense. Right? That said, there's some true value, so I could know what the error is. So what is the error that I'm making in the process is a very good question. So basically, I find my approximations, and question is what is the error that I'm making. So this is an example. Maybe this is my true solution. We're going to actually work on this example. And if I take, in this case, I'm starting from a 0, so I know this point. I'm not making any errors here. And I'm taking this, I basically give myself, oh, I want approximation to my function y on this segment from 0 to 4. I will discretize the segment, and here I'm taking steps of 0.5, and I'm basically going to take here, I'm going to take the derivative, I'm going to take it for a ride up to this point. That's my next point, okay? Now, I'm going to go to my function and find a value of that function f at this point, xi, yi, and I'm going to, that's some slope, this slope, and I'm going to take it for a ride for 0.5. And that's how I keep going. Yes?
How does the step size affect the accuracy?
The smaller the step size, the better. In every iterative method, numerical solution, the smaller the step size, the better. But at some point, there's still a limit to it. And we're going to get examples to it. So here, basically here, I didn't have any error built in my initial condition. That's exact. So here, the only error that I'm making is this, how far of an approximation to the actual function is this slope? How far is my function from its linear counterpart, right? And if it's very far, I'm going to get pretty far. And if I take it for too long. So if I chopped it off here, my error would be much less, right? So at 0.25, this would be my error. At 0.5, this is my error, okay? So the smaller, the better. Great. So basically, but then after I start from this point, now I have a built-in error that I carry from the previous step. And then I'm making more error because I'm again approximating function with the linear part. So I'm kind of carrying the baggage. History matters. And, you know, the baggage can just get me pretty far along the way. So let's just look at this error. Again, I did mention Taylor series. We will not run away from Taylor series in this course. So basically, this would be my Taylor series if this is dy dx for function y. This is y at xi plus 1. This is y at xi. This is dy dx times xi plus 1 minus xi. Right? H is xi plus 1, and so forth. We're basically chopping down this. So this is the error I'm making. Every time I take that linear step for a ride, this is what I'm truncating in Taylor series, so that's the error that I'm making. And I can actually put a bound onto it, okay? So this is what we call local truncation error. I'm truncating the exact expression, and I'm taking only finite terms of it, if you remember lecture 4. Okay? So this is basically the error. And this error is dominated by this h squared term, because if h is smaller and getting smaller, then h squared is much larger than h cubed and much larger than h to the 4 and so forth, which is the rest of the terms. So this is something that we call second order term. Okay? But the problem is that they kind of pile up because they're piling up from previous cases. So this Taylor series really has O of h accuracy. So it kind of changes linearly with h. That's sort of the summary of when history piles up, these terms pile up to an h, O of h. Great. So this is basically what we would get if we had h is 0.25. So I would definitely get closer. Question is, do I get close enough to this function, and am I satisfied with that? Okay, excellent. So basically, quick error analysis. Basically, my round off is always there if I'm storing this in computers, and then I have this local truncation error that I just showed you. Plus, it's propagating. The longer I go, more of it accumulates, and that's basically using this wrong or approximated value from previous step has a penalty. Excellent. We are ready for computational exercise, at least to start setting it up. So before, actually, we'll probably just set it up manually. So let's consider differential equation dy dx is equal. This is really actually just a function of x. But because it's just a function of x, I actually have an analytical solution for it. So we can test against it. Okay? An analytical solution is actually given here for you. So we are going to use this analytical solution to see how accurate we get numerically. So we're going to solve it numerically and compare against analytical. So this is my function. So just as an exercise, take y of 0 is equal to 1. Okay? And let's try solving this for at least one step size on 0, 4. That's actually this particular, this is what we're solving really. Okay. So we're going to start at 0, where my value y is 1. So my x0 is 0 and y0 is 1. So based on Euler's method, what is my y1? What is my x1 if I take h is 0.5? And what is my y1? Take a piece of paper. So I want you to compute this first step, x1, y1, using h is 0.5, which has to be given in the problem. If it's not given, you come up with it yourself. And I want you to find it by hand before we actually go and program. So again, the problem I'm solving is dy dx is, this is my function f of xy, except that it really depends only on x, but that's just a simpler version of this general case. So this is the function f of xy. And this is my initial value. So based on Euler's method, y1 is equal to what? My Euler's method says, in general, my next y is my previous y plus the step size h is my xi plus 1 minus xi, right? And that is here chosen to be 0.5. So if x0 is 0, y0 is 1, what is x1? What is x1? 0.5, so it's 0, which is x0 plus h. Yes? And h is 0.5. Yes? What is x2?
Where is the formula for this one?
My next x is h away. H is my step.
So it would be 1,
Right. So x2 is 1, x3,
1.5.
and so forth. If h was 0.25, then my x1 would be 0.25, my x2 would be 0.5, and so forth. That's my discretization of the x space. Whenever I'm solving for problems numerically, I'm solving in some discretized space. I'm finding some values in some discretized space, right? Great. So what is my y1? It's equal to this value, 1, previous value, which is y0, plus f of x0, y0, times h, which is 0.5. What is f of x0, y0? I plug in x0, y0 into that f there. y0 doesn't matter in this f. My x0 is 0, so this is really 8.5. number. If somebody gave me the analytical solution y, I can evaluate it at 0.5 and see what the true value is, and then see my relative error against that true value, right? Everything we've done so far already. So then I test how far I'm at. I am.
Why is f of 0 and 1 8.5?
Because I plugged in 0 and 1 into that function f.
Into the minus 2x.
Yeah, that's my f. And I don't even have y, so y doesn't matter. I plug in a 0 and I get
Only x. Oh, because we only have x. It's a
Simple
simple
y.
It's a simple thing. It's dy dx.
That's it. Okay? So now you know how to program it, right? We're gonna do that on Monday.
How would you compare, if you have no analytical solution, how would you find your error?
You wouldn't, right? So
mean, yes,
you
yeah.
test your numerical solutions on the cases where you have numerical solutions.
Okay, so you compare it to like data. Like
And you can go and analyze Taylor series. Okay? So you can actually go and analyze this.
Oh, yeah.
So your error is limited by the f prime.
Okay.
And you can put a bound on it.
Yeah.
Okay? So in these cases, this at every step you're making what's called O of h squared error, and as you reduce h, that truncation error is going in h squared, which is pretty good.
Yeah.
However, because you have the propagation, that kind of piles up over your steps, so it piles up to O of h. So Euler's method is not the best. But what you do, and what is done, we will get to actually super accurate methods even in this particular case. And what they do is they optimize how you construct this slope to cancel a bunch of these terms and get to the fourth order. Groups or organize larger groups, but I was like, okay, I'll give a smaller project and just have teams of 2.
Yeah.
And then you have this standard problem where